Hello and welcome to this video about an approximation theorem for continuous functions. And indeed, the idea is really easy to explain. We just consider a continuous function defined on R or even Rn, and then we want to approximate it by using a smooth function. More precisely, we want to do that by using C infinity functions. And there turns out that on compact domains, this approximation converges uniformly to the continuous function. However, as always, before we go into the details and the proof of that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the link in the description, you can download a lot of additional material for the videos. For example, you find quizzes, PDF versions and books that might help you to learn mathematics. And then without further ado, let's immediately start the topic by defining the so-called standard mollifier. In fact, this is a nice C infinity function that also has compact support. This means if you look at the graph in one dimension, it goes smoothly into the zero function. And only on a compact set it has some positive values and it looks like this bump. And indeed, the idea to get that is not so complicated. We just have to use an exponential function to go smoothly into the zero function here. And now the good thing is that this definition also works if our domain is of higher dimension. So for example, in 2 dimensions it would look like this. So we also have a graph of a function that goes smoothly into the zero function. Therefore, we can immediately define such a nice function eta on Rn. And the output of eta is just a real number. And now we know that we just have to distinguish 2 different cases here. The first value, as we have discussed it, is given by the exponential function, and the second value is given by 0. And now in the general case, what we put into the exponential function is given by 1 over the standard norm of x squared minus 1. And this is actually a negative exponent if we consider the case that the norm of x is less than 1. Which also implies the closer we are at the boundary points here, the smaller this whole exponential function gets. And exactly this is the reason it goes smoothly into our zero function. And now the only thing I want to change here is to multiply this exponential function by a constant c. And this positive constant is chosen in such a way that the whole integral over eta is equal to 1. In other words, we just scale the function such that it is normalized in that sense. So you see, I just avoid explicitly calculating this integral for each case n. We know it's definitely possible to calculate the value of the integral over this exponential function, and then the inverse of that number is our constant c. Moreover, now we can also define a whole sequence of functions that look the same, but where the domain gets smaller and smaller when we increase our index. And such a sequence has a special name. It's usually called a Dirac sequence. And for that reason I want to call it delta with index k. And as already mentioned, as before, this will be our eta function again, but in a scaled version. Namely, we scale the peak of the function by our index k. And moreover, we also scale the input x by k, which means the circle we consider here shrinks in radius if k is increased. Or more precisely, the radius is exactly given by 1 over k. So this is something you can already remember. If we increase our n, the graph here gets smaller and smaller, but also higher and higher. And there you might already see that this makes it into a Dirac sequence. But actually a Dirac sequence just is defined by 3 properties. The first one makes everything quite simple because we say every function has to be non-negative. This is definitely satisfied here, and it helps us if we consider the function inside integrals. And indeed the next property already tells us about that. If we integrate delta k over the whole Rn, we should get out 1. And obviously this also should hold for every k in n. This is also satisfied here, and I don't have to show you that because we have the property for eta, and here it's just one substitution inside the integral. Okay, so these 2 properties are not so complicated, but now comes the most important one, the third one. This one tells us that everything for the sequence actually happens in a small epsilon ball. and the common notation for the epsilon ball around the origin is given by b epsilon 0. And for the sake of completeness, I give you the definition here. These are all the points y in Rn that satisfy that the standard norm of y is less than epsilon. So this is just a small open neighborhood around the origin. And there we can consider the integral over delta k. Actually, the better way is to look at the complement of this epsilon ball. So we integrate over everything except the small neighborhood around the origin. And please don't forget, all the integrals we consider here are n-dimensional integrals. And here the picture already tells us everything. If we make k large enough, then everything we integrate over will just be the zero function. Hence, in the limit process k to infinity, we will actually get out 0 for this integral. And this is totally independent of which epsilon we have chosen at the beginning. So you see, these three properties are definitely satisfied for our chosen sequence of functions delta k. However, every sequence of functions that satisfy these three rules we would call a Dirac sequence. And indeed, this is all we need to prove our approximation theorem. And there, as already mentioned, what we consider is a continuous function f. This one is defined on Rn, but it can have values in the whole complex numbers. And then we can just fix any compact set A in Rn, and we restrict f to this compact set. Therefore, f now only defined on A is definitely also a bounded function. Therefore, it makes sense to look at the supremum norm of this bounded function. And here the notation for the supremum norm restricted to the compact set A is chosen with the index infinity and A. So not complicated at all. Here we just take the supremum over all x in the set A. And then we take the absolute value of the function inside at the point x. But now of course we want to know what is the function inside this supremum norm. And there we have our function f minus the convolution delta k with f. And because delta k is a C infinity function, this convolution is also a C infinity function. This means this is the case when we choose this particular Dirac sequence. And now finally the important result of our approximation theorem is that this supremum norm goes to 0 when n goes to infinity. Which actually means that we have the uniform convergence of this sequence of functions to f. However, please note we only have it if we restrict everything to a compact domain. And now for the rest of the video, I would say let's write down the proof of it. So let's first fix an epsilon greater than 0 and a compact set A. Which means on our domain here, we just have to look at a bounded set. And now we know f is continuous, so it will also be a bounded function. Moreover, the restriction to a compact set definitely gives us a uniformly continuous map. This is important because it means in the epsilon delta definition of continuity, we can choose a global delta. More precisely, for every epsilon greater 0, you can choose a delta that works for every x. This means in the case that the distance between x and x tilde may be written as the standard norm of x tilde minus x is less than delta, then we also know that the output has a difference less than epsilon. So this is what the uniform continuity actually means. You can choose the delta independent of a point x. Hence, this is the background information we can use now. In other words, now we can find a real number delta such that for any point in our domain A and y in the delta ball around 0, we have that the distance between two outputs is less than epsilon. So what we put into the function f is first x minus y, and the second point is just x. So by definition, the distance between both points is less than delta, such that the outputs have a distance less than epsilon. So this is what we need, simply because we have the convolution involved. And now we can just calculate our supremum norm as we have it here. So we first look at the absolute value and put a point x in. And now of course we can just use the definition of the convolution. As always, it's simply given by an integral over the whole Rn. And we can write it as delta k of y times x of x minus y. So x is fixed and we integrate over y. And now you can see the idea here is that we also pull f of x into the integral. This is not a problem at all because we can artificially introduce a second integral as well. Namely because we know that the integral over delta k is equal to 1. So here we actually use our second property of the Dirac sequence. And there we can easily pull in our f of x and then we can put both integrals together. Therefore in the next step we only have one integral left. So we have delta k of y inside and the difference of f of x minus f of x minus y. And there you might already recognize that we can use the triangle inequality for integrals to pull in the absolute value. And we don't have to put it around the delta function here because we have the first property of our Dirac sequence, which simply tells us that delta k of y is always non-negative. And so the good thing is that the absolute value is only around the difference for the function f. And now you might already know that we will also use the third property of our Dirac sequence, which actually just means that we will split up the integral into two parts. And we will use our delta from above, but we also use some safety distance, so we use the radius delta half. Hence the second integral on the right will be over the complement of this ball. And there we already have one fact, namely on the left we know that this difference is definitely less than epsilon. So please note this was from the chosen delta from the uniform continuity. And because of the properties of our delta function, we definitely know that the whole first integral here is less or equal than epsilon. So we only have to care about the second integral, and there we already know that we can use the triangle inequality for the absolute value as well. This means instead of a minus sign, we now have a plus sign. This is not a problem at all because we want to have an estimate anyway. And at this point the proof splits up into two possibilities. Either we do the proof for a general Dirac sequence, but then we have to assume that the whole function f is bounded on the domain Rn. And on the other hand, if we use our explicit Dirac sequence given by this eta function, then we don't need to assume any boundedness of f because this whole integral will vanish anyway. And exactly this is what I want to show here, so we choose k so large that the whole support of this delta k function lies inside this open ball. More precisely, we find an index capital K such that for all k greater than this capital K, this one is equal to 0. And that's already it. This shows us that the whole supremum norm is less or equal than epsilon, so we have the convergence. Indeed, the only thing we have to do now is to put the supremum on the left hand side and the right hand side. But obviously the right hand side does not care at all, we still stay less or equal than epsilon. And there we have it, this shows the convergence on compact domains, which implies that the continuous function f can uniformly approximate it by a C-infinity function. And exactly this is the approximation theorem I wanted to show today. So I really hope we meet again in another video about mathematics, and I wish you a nice day. Bye bye.